It's your boy Moonbases. Like, share, subscribe. If you haven't noticed, we're on something else because we got hit. Alright, so we gotta hang out over here for a little while. Mysterious Moonbases. Like, share, subscribe. We're gonna be getting to Bob Lazar, and he's gonna be breaking down how the anti-gravity actually works. I've seen a lot of Lazar videos, but I have not seen this one. This is an older video, and he explains exactly how the anti-gravity technology works, and he mentions the element 115, the mysterious element that has been in question. But first, I'm going to break this down for you. Remember the rocket that was supposed to hit March 4th? Well, I got word that it hit. Scientists think an old rocket just hit the moon going 5,800 miles per hour. Add one more crater to the long list of pock marks on the lunar surface. According to orbital calculations, a rocket hurtling through space for years crashed into the moon on Friday, but the strike wasn't directly observed, of course. And there might be a wait for the photographic evidence. There always is. If they knew that this thing was going to hit, they got enough satellites up there where they could send one around there. China's got one that goes on the other side of the moon. Now, get this. Here's something else that you guys didn't know. All right? This article that I had read, tried saying that the rocket was the Chinese, right? But they're claiming that it's not theirs. So nobody is claiming this rocket. We just said that it was China's. Right here. Space junk crashed into the far side of the moon. A much debated piece of junk suspected to be part of a Chinese rocket that helped launch a 2014 lunar mission hit the far side of the moon, scientists say. The buzz-sized third stage of a Long March 3C rocket was expected to crash into the moon about 7:25. Originally, astronomers thought the space junk was a SpaceX rocket launched 7 years ago. But then the Chinese were saying that it wasn't theirs. Right? Anyway, I was trying to find that. So, yeah, you got the rocket that hit that nobody knows. Nobody's saying whose rocket it was. Chinese is saying it wasn't theirs. It wasn't SpaceX's. So whose rocket was this? And the whole story is suspect. The whole story is suspect. Let's hop over to here to Lazar. Unfortunately, I can't run lives from here yet. So, yeah, I'm going to be in the chat room, though, with you guys during this live premiere. But shout out to everybody, man. Let's get to this. Lazar. This is an awesome, awesome video for those of you that like Lazar. Let's get to it.
One of the most predominantly asked questions is, how is it possible to cross vast expanses of space without exceeding the speed of light? Or how can you travel in reasonable time and economy between points that are light years apart? Now keep in mind that the speed of light is 186,000 miles a second, which translates into roughly 669 million miles an hour. And a light year is a distance traveled in 1 year at the speed of light. Proxima Centauri, which is the star system nearest ours, would take 4 years to reach traveling at the speed of light. So up until now, when we've examined the requirements to travel these distances, we've always had to consider the problems of traveling at a speed near the speed of light. This poses problems with propulsion, navigation, fuel capacities, and even when you consider the effects of acceleration on space-time, which include time dilation, mass increase, length contraction, and a whole host of other things, it quickly becomes evident that this type of travel would require a level of technology that man has not yet achieved. The truth of the matter is that traveling these distances does require a level of technology that man has not yet achieved. But it has nothing to do with flying in a linear mode near the speed of light.
Everyone ready? Disney Plus, Hulu, and ESPN Plus team up.
Oh my God, oh my God!
Epic stories.
We know that the shortest distance between 2 points is a straight line, so in our universe we've always assumed that the fastest way from point A to B was to travel in a straight line at the speed of light. Well, the fact is that when you're dealing with space-time and you enjoy the capability of generating an intense gravitational field, the fastest way from point A to B is to distort or warp or bend the space-time between point A and B, bringing point A and B closer together. The more intense the gravitational field, the greater the distortion of space-time and the shorter the distance between points A and B. Most of us think of space-time as the void or as nothing. And remember, it wasn't that long ago that man considered the air in our atmosphere to be nothing. Yet with time, we've become aware of the elements and properties of the air in our atmosphere. Well, indeed, space-time is an entity, and one of its properties is that it can be distorted or bent by a gravitational field. We know that gravity bends or distorts space-time and light by virtue of the fact that we're able to see stars which we know should be blocked from our view by the sun. Referring to the graphic here, the solid line denotes the position of a star that's located behind the sun, and the dotted line shows its position as viewed from Earth. This is made possible because the sun's gravitational field distorts the space-time and light around the sun, allowing us to view stars which should be hidden from view. We know that gravity distorts time by virtue of the fact that if we take two identical atomic clocks and keep one at sea level and take the other one up to a high altitude, when we bring them both back together, they reflect different times. The difference in this passage of time is caused by the fact that a gravitational field weakens the further you get from the source. So the atomic clock which was taken to the high altitude was exposed to a less powerful gravitational field than the clock which we kept at sea level. The effect of a gravitational field on space-time is something that we've been able to observe, but not to experiment with. This is due to our inability to generate a gravitational field. And up until this point in time, great mass such as a star, planet, or moon was the only source of a discernible gravitational field that we're aware of. So just as the gravitational field around great mass such as a planet distorts space and time, any gravitational field, whether naturally occurring or generated, distorts space and time in a similar manner. Now, the great benefit of generating an intense gravitational field is not only can you turn it on, but you can turn it off. If we refer back to our original illustration of space-time distortion, we can see that when we generate an intense gravitational field, we can distort the space-time and in turn the distance between the point where we are and the point where we want to be. We can then position ourselves at the point where we want to be and then stop generating the gravitational field, allowing space-time to return to its natural form. In this manner, we can travel great distances with little linear movement. And this is how space-time distortion translates into reduced distance. Now back to our original question, how is it possible to cross the vast expanses of space required for interstellar travel without exceeding the speed of light? This is accomplished by generating an intense gravitational field, distorting space-time and allowing you to cross many light years of space in little or no time and without traveling in a linear mode near the speed of light. So we've learned how space-time is distorted by a gravitational field, we've learned how that gravitational field is generated, and we've also learned where you get the power to accomplish all of this. Now it's time to link all we've learned in our science lessons to the vehicle that utilizes all of this technology. And a few years ago, I never thought I'd hear myself say this, but that vehicle is a disk, which is generally referred to as a flying saucer. I had at least partial views of the 9 different disks out at Area S4, but the one I'm going to describe to you now is the one where the density of the gravitational field around the disk increases.
It's your boy Moonbases. Like, share, subscribe. Lazar covering anti-grav. Hopefully we don't get hit with a copyright on this. I got this from another site who got it from another site who got it from another site, so there shouldn't be any issue on it. It's your boy Moonbases. Like, share, subscribe to this new channel, please. We are getting attacked from all angles. All angles. They do not want me speaking at all. Let's get back to it.
Distortion of space-time around the disk also increases. And if you could see the space-time distortion, this is how it would look. As you can see, as the output of the gravitational field from the amplifiers becomes more intense, the form of space-time around the disk not only bends upward, but at maximum distortion actually folds over into almost a heart shape around the top of the disk. Now remember, this space-time distortion is taking place 360 degrees around the disk. So if you were looking at the disk from the top, the space-time distortion would be in the shape of a donut. When the gravitational field around the disk is so intense that the space-time distortion around the disk achieves maximum distortion and is folded up into this heart-shaped form, the disk can't be seen from any vantage point, and for all practical purposes is invisible. All you could see would be the sky surrounding it.